Hello, my name is Sunwoo Kim, and this is my lab report for Lab 3. This report will consist of an introduction, principles, Part 1 code, Part 2 code, results of discussion, and a conclusion. This lab focuses on black holes and orbits. Part 1 is a computational model of a star orbiting a black hole. The goal is to analyze the star's motion to estimate the mass of the black hole. Part 2 is a computational model of a spaceship in orbit around a planet and its moon. The goal is to simulate a figure-8 shaped orbit and determine the initial velocity required for the spaceship to orbit both the planet and the moon without crashing. The overall purpose of this lab is to utilize Newton's second law and how it relates to momentum to simulate orbits and calculate the mass of a black hole. The mass of the black hole was found to be approximately 1.38 times 10 to the 34 kilograms, and the initial velocity of the spaceship was found to be negative 24,000, 31,000, 0 meters per second. The fundamental principles for this lab include Newton's second law in terms of momentum. Net force equals the change in momentum over the change in time. F net can further be broken down into the sum of its parallel and perpendicular components. F net parallel can be calculated by d magnitude of p over dt times p hat. Newton's second law can also be derived into the velocity update and position update formulas as shown. Another key formula needed is universal gravitation, which is g big M little m over r squared times negative r hat. This is my code for part 1. The system is the star and the surroundings are the black hole. I entered my seed, which is my Georgia Tech email, and this generates me a unique star trajectory. The gravitational constant is defined. The mass of the star is 2 times 10 to the 30 kilograms. Delta T is 86,400 seconds, and we're starting at T equals 0. This is my calculation loop. First, we calculated initial and final momentum using the initial and final velocity of the star. Then we can calculate the change in velocity and change in momentum, and therefore the change in momentum over the change in time. Then, applying the momentum principle, we know that the change in momentum over the change in time equals F net, and we can move on to calculate dp dt parallel using the formula covered previously. We can subtract it from dp dt to find the perpendicular component, and these are also equal to the parallel and perpendicular components of F net. Finally, to calculate the mass of the black hole, I rearranged the universal gravitation formula to solve for the mass of the black hole at each data point. I have also added arrows to depict F net and its parallel and perpendicular components. The output is shown here. Masses were outputted from over 400 data points, and I took the average to get 1.38 times 10 to the 34 kilograms. This is my code for part 2. The system is the spaceship and the surroundings are the planet and its moon. All their masses, along with the gravitational constant, are defined first. Delta T is 60 seconds, and we start at T equals 0. T max equals the number of seconds in 1 month. Then, the moon's initial speed and velocity are calculated, and there is a section to define the ship's initial velocity. This is where we'll plug in values to see what works and what doesn't. This is my calculation loop. Using the universal gravitation formula, I calculated the net force on the spaceship and the moon since those two are being acted upon. Then, using the velocity update and position update formulas, I can predict the motion of the spaceship and the moon based on what forces are acting on them at each point. Pause now to take a closer look. After many rounds of trial and error, I achieved an orbit as shown on the right that continues on for a month without crashing. The initial velocity required for this was negative 24,000 meters per second in the x direction and 31,000 meters per second in the y direction. The spaceship's orbit is affected by both the moon and the planet, and it is ultimately orbiting around both of them. However, you may notice that the orbit is not a perfect figure-8 shape. Therefore, we must cover possible sources of error. The first source may come from approximating the star's mass in part 1. We used an average of the star's mass calculated at numerous data points to get an estimate. Also, this is a simulation and not real life. The second source may come from using trial and error to determine the spaceship's initial velocity in part 2. Coming across a one perfect answer is very difficult. My spaceship is able to orbit both the planet and the moon without crashing, but I did not get a perfect figure-8 orbit. Here are some concluding questions. How is the net force and its components different from the rate of change of momentum and its components? Although the respective components are equal as stated by Newton's second law, the way you calculate the two differ. Net force requires you to find and calculate all external forces acting on each component in the system, whereas rate of change of momentum just requires you to observe the changes in motion and use values like velocity, mass, and time. What if you wanted to predict the motion of the entire system, including a black hole, star, planet, and moon? What would you need to include in your computational model? Would there be any dominant interactions? Our model would have to include calculations for the force of universal gravitation of each object in the system on all other objects in the system, and then sum up the net force acting on each object separately. The mass of the black hole is the largest, so gravitational interactions including the black hole will be dominant.